everybody, welcome to Monte Carlo Methods. My name is Jem and I will be your guide this semester through Monte Carlo Methods, and I'm really glad to be here because this is what I do. This is my area of research and my supposed area of expertise. So I want to take you from as close as I can to ground zero up through all the major algorithms and then some of the much more recent algorithms, and even in the last week or two, some completely new algorithms that are probably not even published yet at that time. So I hope you stick around to get to that very exciting point. And to take this course, you do need to know some probability. Hopefully you've heard of a probability density function, expectation, distributions like the exponential distribution, the binomial, geometric, things like that. And to fully grasp this course, you will need something more like mathematical statistics. And the reason is that we're going to talk about algorithms, and even if you have not had mathematical statistics, if you need to use Monte Carlo algorithms for your research or your job, each and every day, almost every day, you're going to get a new algorithm for your toolkit, what it's for and how to use it, and you'll be just fine. But in this course, every time I present an algorithm and tell you, if you do this, you will get this, I want to also prove that that's true. And that's going to require mathematical statistics and maybe some other slightly more advanced math than your basic probability course. But again, you could ignore that stuff and still take away algorithms from this course that you'll be able to run for your own problems. So let's get right into it. What are Monte Carlo methods? Monte Carlo methods are algorithms for solving what would otherwise be intractable problems by introducing randomness and repeated experimentation. So as a motivating first example, let's try integrating with darts. As my example, I've got a rectangular dartboard, which I realize is a little strange looking, and I'm going to assume that I can throw darts completely at random at this board. So that means that I'm not going for the center, nor am I likely to hit the center. I've got a bunch of equal area subrectangles here, and if I'm throwing the darts completely at random, I have the same chance of ending up in this rectangle as I do this rectangle or any other subrectangle here. Furthermore, this statement is still going to hold if I make the mesh of rectangles finer or coarser, or if I throw them out completely and just consider a funny shape in the rectangle with some area, and then a second funnier shape and different shape with the same area in the rectangle. The probability that my dart hits one of those shapes is the same as the probability of hitting the other equal area shape, even though it's a completely different shape, if that makes sense. So in other words, I have the same probability of hitting any two subregions of any shape as long as they have the same area. In mathematics, and especially in probability and statistics, we say that we're throwing the darts uniformly at the board. So at random and uniformly mean the same thing here. So what does this have to do with integration? I'm going to put my dartboard on the xy axis between x equals 1 and 3 and y equals 0 and 4. And I didn't draw the pattern, but here's my dartboard. It's just a rectangle sitting in the xy plane. Now imagine I can throw darts at random or uniformly at this rectangular dartboard, and consider the subrectangle consisting of the lower half of this rectangle. What is the probability that my dart is going to hit down here? So this is exactly half of the rectangle, and I have an equal chance of hitting up here and down here. Therefore, the answer, the probability I'm going to hit this subrectangle, is 1/2. Let's do something just a little more interesting. Here I've drawn a circle with radius 1/2. I don't know exactly where the center point is, but it's such that the circle is completely contained in the dartboard. Now throw a dart at random or uniformly at the rectangle. What is the probability it hits the circle or lands in here? The answer is the relative area versus the total area of the rectangle, which is pi times 1/2 squared divided by 2 times 4. Again, this is throwing darts uniformly or at random at the rectangle. Now let's get back to integration. Consider a function y equals f of x, and suppose it looks something like this. I'm going to choose 2 points a and b on the x-axis, and I want to integrate this function from a to b. I'm going to call this integral I. So capital I is going to be the integral from a to b of f of x dx. And if we envision this on here and I put down an a and a b, given that this function is non-negative, this integral is going to represent the area under the curve between a and b. I want to throw a dartboard down here. so that the total area of interest, the yellow part, is completely contained in the rectangle. So I'm going to make the left edge of my rectangle at x equals a and the right edge at x equals b. And at my y, or my base of my rectangle, I'm going to put it 0, and the height is going to be at some number c, which is up above the function. And we'll talk more specifically about how you might choose this c later on in the course. But the idea is this rectangle completely contains the region of interest. So now I'm going to throw a dart uniformly or at random at this rectangle. And what is the probability that that dart lands in the yellow region? In other words, under the function y equals x. I'm going to call this probability lowercase p. So little p is the probability that the dart lands under the curve. And because we're throwing the dart uniformly, we know that little p is the area under the curve, which is I in this case, divided by the total area of the rectangle. So I'm assuming we don't know I, and therefore we probably don't know p, but we do know the area of the rectangle because we chose that rectangle ourselves. And I want to use this relationship to try to approximate I. We're going to do this by throwing not one, but n different darts at the rectangle. And if we repeatedly do this, there's your repeated experimentation, and we count how many darts land below the curve or in the yellow part of this rectangle, then we can estimate p with an estimator that I'm going to call p hat, which I'm going to define to be the total number that land under the curve divided by n, the total number of darts thrown. And now we can use our relationship between p and I to come up with an estimator for I that I'm going to call I hat, which is going to be p hat times the area of the rectangle c times b minus a. This is a Monte Carlo estimator for the integral I, and it's our first example of a Monte Carlo method. I'm not saying you want to use Monte Carlo integration in a problem like this, so presumably we cannot do this integral analytically, but we can use numeric approximation, numerical quadrature quite easily. But Monte Carlo, number one, it's just an example. But number two, it's actually going to become quite a relevant example when we talk about high dimensional integrals and when sort of splitting things up in a quadrature type approach and high dimensions becomes quite expensive, which used to mean we didn't have computing power for it. Today we do, but it means quite tedious. Again, it's just an example of a Monte Carlo method where we've introduced randomness and repeated experimentation to a problem. In this problem, we didn't have randomness to begin with. We had a deterministic problem, but it might be that our original problem also involves probability, and that's okay. So Monte Carlo methods were first developed by a Polish physicist and mathematician named Stanislaw Ulam, and he lived between 1909 and 1984. He was, as I said, a physicist and mathematician, but an eventual computer scientist as well. Computer science was not a big thing in the early 1900s, so this was the later part of his career. He was invited from Poland to visit the US, and he became a visiting scientist at Princeton and Harvard and at various institutes they had in the area, and this was circa 1935. He went back and forth for a long time between the United States and Poland, but eventually fled to the United States permanently to escape the German invasion of Poland. He was first invited by John von Neumann, who was eventually a good friend of Ulam's and colleague, and von Neumann invited Ulam to work on the Manhattan Project at Los Alamos Labs around 1943. In 1945, Ulam became an associate professor at the University of Southern California, and it was less than 6 months later that he suffered an acute attack of encephalitis. His brain was swelling and he needed emergency surgery, which is never a good thing. He, his colleagues, his friends were especially worried that he would never be able to do mathematics again, and that was not the case. He eventually recovered after a long road and convalescing in bed for a long time and playing a lot of games of solitaire. It's actually said that he came out of the other end a different kind of mathematician, a more applied mathematician as opposed to theoretical. This is said. I have no place. I have nothing to cite for this, but it is said that he came out a more applied mathematician with a lot more conjectures which led to some really great discoveries. So he was more experimental after his head injury. But as I said, he played solitaire for a long time while convalescing in bed, and he began to think about the probability of winning a game of solitaire. So if you don't know what solitaire is, without going into it too much, you have a deck of cards and you have them laid out in certain stacks, and you want to reorder them according to certain rules until you've achieved a final ordering. And it's not always possible. Sometimes you get stuck and there are no more moves. And Ulam started to wonder what was the probability that a game of solitaire is winnable. So to answer this question, it seems like a crazy question of probability. There's not just randomness and shuffling, which is not that bad, but with each and every decision you make, the whole game is changing and the possibilities for what comes after changes. So to try to answer this question of probability analytically is next to impossible. But Ulam started to think about playing again and again and again. I wonder where he got that idea. I think he was playing an awful lot. And keeping track of the number of games won versus the number of games played so that he could estimate the probability of winning a game. He went back to Los Alamos eventually and shared this idea with his friend von Neumann, who was very excited. Now, it doesn't hurt that it was 1945 and the University of Pennsylvania had just developed the world's first digital computer, known as ENIAC, which was an acronym for Electronic Numerical Integrator and Computer. And for Monte Carlo methods and the idea of sort of simulation and throwing random darts at things, this could actually work. And Ulam and von Neumann really took off with the idea, and a lot of other people that we're going to talk about this semester jumped in early on, and Monte Carlo methods were born. So now I want to go back to the function we were trying to integrate from A to B and the rectangle we put around that function and ask you a question. How can we throw those darts at that rectangle? How can we make a computer throw those darts for us? That is, how can we uniformly and at random select points from the rectangle with base A to B and height from 0 up to C? As a partial answer, I could tell you this. We can, number 1, select an x-coordinate uniformly between A and B, and then number 2, select a y-coordinate uniformly between 0 and C, which really doesn't answer the question because we don't know how to do either of these things. But we're breaking down the problem to a smaller problem. And before I answer these questions for you, I'd like to talk about something seemingly unrelated. Let's take a break and talk about simulation of random variables and what it means. As an example, I'm going to start with everyone's favorite continuous random variable. I'm going to let x have an exponential distribution with rate lambda. This means it has a probability density function with some parameter lambda, and the probability density function is lambda e to the minus lambda x, which looks like this. It starts at lambda and goes down exponentially. As you know, the probability density function for a continuous random variable does not give us probabilities for that random variable, but it is a curve under which area represents probability. So if I want to know, for example, the probability that x is between A and B inclusive, then I want to integrate this PDF from A to B. Similarly, if I want to know the probability that x is strictly between A and B, I still want the area under the curve between A and B, and because there's no area in these two vertical lines, I still want to integrate from A to B. So this integral is going to give us this probability, or I can take out one or both of the equalities here. So the question in front of us now is, what does it mean to simulate values for this random variable? Not how to do it, but what does it even mean? What I want is some sort of algorithm that will spit out a list of numbers like 0.3217433 and 1.0456102, etc. List of numbers. And what do these have to do with the exponential distribution? Note that, for example, just to pick an interval out of the air, the probability that x is between 1 and 2 is the integral of the PDF from 1 to 2, and this turns out to be e to the negative lambda minus e to the negative 2 lambda. And lambda is some parameter, and let's assume it's fixed and known to us, so this is just a real number probability. I want my algorithm to produce a list of numbers over here, so that the long run proportion of times that I get numbers between 1 and 2 is equal to this real number probability over here. And I want this to be true of any interval I might choose to check via integration. And that's going to be hard. There's, an uncountably infinite number of intervals we'd want to check with integration versus the proportion in this list. But that is the idea. I want an algorithm that will produce a list of numbers that will have this kind of property where the long run proportion of times you're in various regions matches what it should be for the random variable x. So in order to see this happening without having to check every possible region, it is useful to make a histogram of your numbers. So I am going to put these numbers down, at least the first 3 that I have here. Let's say that's all I've got so far. My algorithm is going to keep spitting out numbers, but I have 3 so far. And I am going to make a histogram. So for making a histogram, you have to choose some kind of bin width. And for this picture, although I don't really have a scale here, I've chosen a bin width of 0.1. And the bins have fallen such that each one of these points is in its own bin. And right now, when I look at this list of 3 numbers, a histogram for this list will put one number into each of these bins and give us 3 rectangles with an equal height. Now, if I continue with my list and put in more and more numbers, I'll get more rectangles, and some will get larger, some will get smaller as there's multiple values in a particular bin. And eventually, we will get a shape that kind of matches the PDF, the probability density function, if the y-axis is scaled appropriately. Remember, the PDF is a curve under which area represents probability, and we want our histogram areas of the rectangles to also represent the probability of seeing a number in that particular bin based on what we've seen in our sample. So what can you do for the y-axis when building a histogram? You basically have 3 options. Number 1 is that your y-axis could have counts or frequencies. So this is where the height of the bar is the total number of values in your long list generated that fell in the particular bin of interest. The second thing you can do for your y-axis on a histogram is have your y-axis represent proportions or relative frequency. So if you're looking at a bin between 0.1 and 0.2 on the x-axis, you could look at your long list of numbers and compute the proportion of values you have between 0.1 and 0.2 and make your bin height that value. That would be relative frequency or proportion on the y-axis. But the third option, and the option we want to use, is to use what is known as density on the y-axis. And this is where you make the height or the values of the height of the bars such that the total area of the bar represents the proportion of values in your list that was in that bin. So if you're looking at a bar on the x-axis between 0.1 and 0.2, and maybe 47% of your values fell in there, then you want to make the height such that the height times that bin width of 0.1 gives you 0.47. This is how you make the bar have area 0.47, which matches the area under the curve between 0.1 and 0.2 if your algorithm is working correctly and you have a histogram made with a lot of data. Because you want to see the right probability of being in each section. The PDF gives you probability representing area under the curve, and we're specifically making our histogram using density on the y-axis so that the area of the bars represent the probability of seeing certain values based on what we have in our sample. Density can be computed as relative frequency divided by bin width, and we're going to see how to do that in this class. But what is the algorithm supposed to do? It's supposed to give you a list of numbers. You're not going to see anything exponential looking about it or probability looking about it until you have a lot of numbers, and then you can see that all the areas match up if you look at it graphically with a histogram, at least as a first pass for what you're doing is correct. And we're going to do testing in here for figuring out whether our results are correct or not, but a first pass would be to look at it with a histogram. That said, we still don't know how to generate those numbers. We still don't know how to simulate or generate values or realizations or observations. Observations, realizations, these are the same things. Simulate, generate, same thing. We know that if our algorithm is working well and we make a histogram of our results and we put the right scaling on the y-axis, the histogram should match the PDF. But we don't know how to get those numbers. And we still don't know how to get the numbers in the uniform case. We don't know how to simulate, draw, generate, produce observations, produce realizations from the rectangle uniformly, which we broke into two steps, generating uniformly on the x-axis and the y-axis. So we broke a two-dimensional problem into two one-dimensional problems. But how do we do that? Both of these tasks can be achieved if we can simulate values uniformly on the interval between 0 and 1. We can then adjust and scale and stretch and translate things to get those values uniform between numbers like A and B, and then we can do further manipulations to get those numbers to look more like numbers coming out of an exponential distribution. But everything we do this entire semester is going to boil down to being able to generate or simulate or sample observations or realizations from the uniform 0-1 distribution. As a reminder, the PDF is just a flat line. It's saying that you're equally likely to be anywhere. So if you look at some interval of some length and you move that somewhere else, the total area is going to remain the same because the PDF does not go up or down. It's a flat line distribution. The PDF is 1 between 0 and 1 and 0 outside. And if you had an algorithm that could generate, simulate, sample values, realizations, observations from the uniform 0-1 distribution, then what you should get if you make a histogram and you put density on the y-axis, you should get a histogram that kind of is trying to match that flatline PDF. If you have a small sample, it's not going to look so good. A large sample, it's not going to look so good if your algorithm's not working, but if your algorithm is working, then it should start looking like it's trying to match that PDF. I claim that if we can do this, if we had an algorithm that could generate these numbers for us, we can turn them into those numbers from the exponential distribution and anything else we want to in this course. And we produce these values, simulated or sampled or generated values or observations or realizations from a uniform distribution on the interval from 0 to 1 using a random number generator that is going to be built into whatever software you want to use for this course. I have been asked to teach this course using R. R is statistical software. It's free, it's easy, and it's powerful for statistics and other things. I personally love it for visualizing things and cool interactive graphs. I have to admit to you that it is not my software of choice for Monte Carlo algorithms. And the reason is that Monte Carlo algorithms are very grindy and loopy with millions of repeated loops and things, and R is not good at this. So I would use Python if it were me, but I was asked to use R this semester, and I think it's fine. But if you're serious about using Monte Carlo in your own research or work, it might not be fast enough for you, but it's going to be easy for us to get up and running with quickly and understand. So we're going to use R in this course. By the way, when I do my own Monte Carlo algorithms with something like Python or even Fortran, an ancient language like that, I usually take my output and then feed it into R to take advantage of the great graphics and visualization tools that R has. So I definitely use R every single day as well. But again, Monte Carlo is grindy and loopy, and R is not so good for that. But we're going to make it work. So a random number generator produces values sampled from the uniform 0-1 distribution. And these values are going to turn out to be the base units or building blocks for all of our Monte Carlo methods. I'm going to touch briefly today and maybe in our next class on random number generators that are built into software, but I'm not going to spend very much time on it at all. So the reason I'm not going to spend very much time on it at all is because it is a completely different subject. We can spend an entire semester, and it's more of a computer science kind of course than a probability and statistics course. We can spend an entire semester on random number generators, but it's not what we're here for. The point of this course is what we can do with the numbers that come out of a random number generator. It's a completely different subject, and I don't want to ignore it completely because it is our base for everything, but I'm not going to do it justice. I'm telling you that right now. So the vast majority of this course is going to focus on what we can do with these numbers, but let's talk a little bit about software and random number generation. There are generally considered 3 types of random number generators out there. Really, it's only 2, as you'll see. The first type is a true random number generator, usually abbreviated or with the acronym TRNG. And this is where you are using some actual source of physical randomness. So for example, you might be measuring radioactive decay with a Geiger counter, and this is giving you random clicks. And you could do several things with this. You might compare consecutive interclick durations, and you might say something like, if this click is longer than the previous click, I want to output a 1. And if a click is shorter than the previous click, I want to output a 0. And if you do that, you'll get a bunch of 1s and 0s, which will be binary numbers that you can use to generate numbers between 0 and 1. Radioactive decay is considered truly random. I am not going to give you my opinion on that or try to convince you of that, but that's certainly a sort of standard example of a physical random source that can be used to generate random numbers. True physical random number generators are also called hardware random number generators. So when you see that, it's not actually referring to the hardware that is your computer. Hardware just means it's a physical random number generator. The second type of random number generators that we are going to talk about in here are known as pseudo-random number generators, affectionately abbreviated as PRNGs. So this is going to be an algorithm that tries to mimic randomness, and it's actually completely deterministic. So we're going to start with a number, and then we're going to do this to it, and then we're going to do that to it, and we're going to get another number, and then we're going to repeat. And the goal is to get out numbers that appear to be realizations or observations from a uniform 0-1 distribution and appear to be independent, which sounds crazy. It is an algorithm. You plug in a number, you get out a number. You plug in the same number, you get out the same number. There's definitely dependence there and nothing random about it. So this sounds crazy, but if you do it well, you can mimic randomness. And we are going to do examples of pseudo-random number generators today. And I'm going to try to convince you that they're not so bad, depending on your application. If you're doing something that is a matter of national security or something that needs to be cryptographically secure, maybe you want to be careful. But for the most part, pseudo-random number generators that are built into all numerical software are going to be what you're going to be using for your Monte Carlo methods. So the third type of random number generator is not even really trying to be a random number generator. It's known as a quasi-random number generator. We're not going to spend really any time on this at all, but we're going to see when we look at pseudo-random number generators next time that some of them are, well, they're all trying to generate numbers between 0 and 1, but if you run them a long time, some of them actually will have some holes in the interval that are never hit. And the goal of a quasi-random number generator is to systematically and deterministically fill in holes. So this will make more sense next time when we see an example of these holes that are being left by pseudo-random number generators. And at that time, I will mention the quasi-random number generator one more time, but we're really not going to go into it. So I hope to see you next time where we talk about pseudo-random number generators and the kinds that we're going to be seeing and using in this course as we go forward. I hope to see you in the next one.